Hello guys, welcome to lesson 2 of bonding. Lesson 1 we looked at ionic bonding. Lesson 2, as I promised, we're going to go through covalent bonding. We're going to follow a similar template with our definition, our simple example, describing what is happening, and then using some diagrams to demonstrate this. Covalent bonding is a little more advanced than ionic bonding because then we need to look at simple and giant covalent structures and the difference between these. Okay, so as similar to last time, let's start with our definition of covalent bonding. So if you remember, in the last lesson, we looked at ionic bonding. That is a transfer of electrons between our metals and our non-metals, using magnesium and oxygen as our example. From your homework, you would have looked at the transfer of electrons and the forming of this ionic bond between sodium and chlorine. Please check the Google Classroom for your feedback on this. Okay, so covalent bonding. We have the bonding between non-metal and a non-metal, and we are forming this. Oh, do I have enough room? Yeah, we've got to squish in there. A covalent bond. Okay, so how do they do this? We need some key terminology once again, similar to our ionic bonding, but this time we're not transferring, losing, gaining electrons. We are simply having the sharing of electrons. Okay, this one's a little bit more technical. You need to be able to use and read the periodic table in order to complete these tasks. So I think it would be a little bit more helpful for this lesson if you pulled up your periodic table. That is also in the Google Classroom for you to refer to any information that we discuss in here. The examples we'll be looking at first for our simple covalent bonds is our one for one nitrogen, 3 hydrogens bonded together to form our ammonia. And our second one, we're going to have our 1 carbon bonded to 4 hydrogens, forming our methane. So there we go. We can simply, we need to be able to read the amount of elements within these structures for our simple covalent bonds. No number on our nitrogen here, so simply representing 1. Our small 3, identifying that we're going to have 3 hydrogens bonded to this 1 nitrogen, and the same for methane as well. So it's always nice to work through this methodically like we do in the classroom, so we can identify each stage and what is actually happening. So we mentioned this 1 nitrogen, so what we're going to do and what you're going to do at home is refer to your periodic table, and within the center of your piece of paper, or if you've laid it out like me here, simply draw your electronic structure for nitrogen. You can pause the video now. Okay, right, so nitrogen in our periodic table here, we want to identify that. So let's just write this out so you can refer to it as well. Atomic number of 7, atomic mass of 14. So recap once again, our atomic number is going to tell us the number of protons and electrons, and that is what we want to refer to once again within our bonding. So drawing out the atomic structure, let's be nice and simple. Again, our nucleus with our nitrogen. Don't be too concerned about writing the number of protons and neutrons in here just yet. We want to identify the number of electrons. So we're following a similar pattern that we learned in class. First orbit is going to be able to hold 2 electrons. Our second orbit is going to be able to hold a maximum of 8 electrons. But how many more do we need? So our atomic number of 7. So 1, 2, 3, 4, 5, 6, and 7. Okay, there we go. So there we have drawn out our electron configuration, our atomic structure for nitrogen. Let's take this one off the board. Okay, hydrogen. Okay, very, very unique element here. So we need to identify that we want to bond 3 of these hydrogens to our nitrogen to form this covalent bond. So hydrogen here, atomic number of 1, atomic mass of 1. So we have 1 electron in the outer shell. So similar to ionic bonding, we want to create this full, stable outer electron orbit. So we need 3 hydrogens to bond to this nitrogen. Where is the space upon your atomic structure of nitrogen that is able to accept these hydrogens? Please pause the video now and identify this. Yes, correct. So we have our space here, we have this lone area, we have this space here, and we have this space here. Because electrons, they work in pairs, and we want to be able to share our hydrogens here. Keyword, sharing of electrons within covalent bonding. So we are going to have a situation where we're going to have, that's what our H in here for our nucleus, our hydrogen, and we are going to have the sharing of an electron here with our hydrogen like this. Another one, we're going to have one more in here. Let's just represent with our hydrogen. One more in there. One more in here. Oh, hydrogen. And let's put it in there. So let's add things up. So our nitrogen, we now have 1, 2, 3 shared electron, 4 shared electron, 5, 6 shared electron, 7, 8 electrons, creating stable outer shell. But what about hydrogen as well? Hydrogen can also share the electrons from nitrogen. It's sharing this electron here, so hydrogen can have this full stable outer shell with its 2 electrons. Same here and same here for a simple covalent diagram. There's 2 types of diagrams we want to be able to identify. Here we have what we call our dots and cross diagram. Hopefully that is quite self-explanatory why it's called a dot and cross diagram. We have our dots and we have our crosses showing the sharing of electrons. There's also another diagram you need to be aware of called our stick or our line diagrams. They're a lot more simple to do. So once again, for our ammonia, NH3, we can show that we have our 1 nitrogen bonded to that with our lines. We can have our line diagram like this, nice and simple. Okay, we said we were going to work through 2 examples, so that's number 1 done. Our second one is for our methane, 1 carbon, 4 hydrogens. Using that template from our ammonia, please attempt this one yourself. You can pause the video now whilst you do this work. Okay, so hopefully you were able to use this template. So let's have a look once again, similar to our ammonia, but now we have 1 carbon and 4 hydrogens. If you follow the same template that we looked at before, we can have our carbon. First shell, let's refer to our periodic table. Atomic number of 6, atomic mass of 12, so let's put our information in. Atomic number 6, therefore we have 6 electrons, 2 in the first orbit, 4 around the outside. And now doing that, you'll think, okay, I get this, no problem. 4 hydrogens, they're going to share their electrons with our spaces around here. So same situation as before, dot and cross diagram, dot and cross with our hydrogen here, dot and cross once again, nice and simple, dot and cross, here we go, dot and cross. Wow, isn't that so simple? Why is it called dot and cross diagram? Well, we have our crosses, we have our dots, 1 carbon, 4 hydrogens. Carbon can have its full stable outer shell. Let's check 1, 2, 3, 4, 5, 6, 7, 8. Happy with that. Hydrogen can also have its full stable outer shell from its first orbit. 2 electrons, one shared from the carbon and one from the hydrogen, allowing hydrogen to have its stable orbit. 1, 2, 1, 2, 1, 2, 1, 2. Nice and simple. Okay, so just a quick recap. Covalent bonding, we had a non-metal and a non-metal forming this covalent bond. It doesn't involve, the key terminology here, unlike ionic bonding, we were transferring these electrons. Covalent bonding, we are sharing these electrons. And we showed how the sharing of electrons can take place for our ammonia and for our methane. Okay, nice and simple. Giant covalent bonding involving the bonding of multiple, lots and lots of carbons. This is a bit more technical, but we'll work through the nice simple template again, which will allow us to make sure we can get all these marks within our exams. So key information we need to know about the diamond. Well, diamond is covalently bonded using carbons, and graphite, similar, covalently bonded using carbons. However, one vital piece of information within our diamond structure, one carbon is covalently bonded to 4 other carbons. And you can kind of visualize that in your head, this structure that is being created from when we had our 1 carbon in the middle here, we had our 4 outer shell electrons. We are going to be sharing the electrons with other carbons, allowing this covalent bonding within this mass structure. So diamond is very, very high, very hard, has a very high melting point due to the forces that are holding this structure together. Graphite, on the other hand, graphite is bonded to only 3 key term other carbons. Okay, so situation, let's have a look. So carbon, nucleus, first orbit, 1, 2. Refer to your periodic table again if you need to. Carbon, atomic number of 6. Therefore, outer shell electrons, 1, 2, 3, 4. Let's just check back, make sure we're happy. 1, 2, 3, 4, 5, 6. Yes, that's good. Atomic number 6, electron 6 here. What do I mean by graphite being bonded to 3 other carbons? Well, we're going to have a sharing of electrons, or the covalent bond formed between an electron here, an electron here, and an electron here, leaving 1 spare electron. And this is what makes graphite so unique with its properties. What is happening now with this 1 electron? It is going to be donated into a sea of delocalized electrons. A very difficult term. If you watch the next video on metallic bonding, you'll be able to gain a further understanding about this. But we are losing this 1 electron, and this is the electron that is going to be able to conduct electricity, and it conducts thermal energy. So in your chemistry lessons, when you will look at electrolysis within your GCSE course, they often use graphite as the electrodes because they can conduct electricity. Within your art lessons, you will use graphite pencils, and when you're using them a lot, you'll find they heat up quite fast because they can conduct this charge because of this free electron here. Okay, thank you for your attention watching these videos on covalent and ionic bonding. Lesson 3, we will look at metallic bonding.